Let's go over the different values of first and second derivative of a function and its interpretation. So let's start with the functions that are increasing. A function can be increased in three different ways. Let's sketch it here. One is linear increase, one is increase as a curve this way, and one is a curve this way. What is the first derivative of this function? First of all, the function is increasing in all three types, so the first derivative will be positive. When the increase is linear, the gradient is constant all along this interval. And the first derivative will just be a horizontal line to denote some constant m. Second derivative will just be 0. The derivative of constant is 0. Second type of increase, we can see that the gradient here is positive and it is increasing. First derivative looks like this. Positive, increasing. We don't know exactly how it is increasing. It could be this way or this way, but it doesn't matter. We know that first derivative is positive and increasing. Here it's also positive. It's positive and increasing. So second derivative, since the first is increasing, second derivative will be positive. Here on the third type, we can see that the gradient is always positive, but it is decreasing, becoming smaller and smaller. If this is 5, then this is 4, 3, 2, it goes down with positive numbers. Okay, this is positive decreasing. So when first derivative is decreasing, second derivative must be negative. That's the gradient of the first derivative, which is negative because it is decreasing. This shape is called concave up, since the gradient goes up, increasing, and this shape is called concave down, since the gradient goes down, it is decreasing. Let's go to the next three cases where the function is decreasing. It could decrease this way as a linear line. It could decrease this way or this way. Again, here we have a constant gradient for the function, which is negative. The first derivative will be a constant, a horizontal line for a value, some value that is negative. Second derivative is derivative of a constant, it will be 0. When the function decreases this way, we can see the gradient always negative since it is decreasing. We can see that the gradient is decreasing in absolute value, but since the values are negative, it is becoming larger and larger. This is minus 5, this is minus 4, minus 3, minus 2, minus 1. It is becoming less and less negative. The first derivative that describes this gradient will look something like this. Negative, but increasing from -5, -4, and so on, going up towards 0. So we have first derivative, which is negative, increasing. So the second derivative here will be positive. And for this shape, we can see that the gradient is negative, that becomes more and more negative. It means that it is going down, something like this. Okay, this is -1, -2, -3, -4, becoming more and more negative. The function, the first derivative, is decreasing. So second derivative must be negative here. So this is when the function is increasing or decreasing. Let us go to the cases where the function is a constant, doesn't change. So we could have an interval in which the function is constant. This is where the gradient of the function is 0 all along. So first derivative will be just 0. And of course, second derivative will also be 0. But sometimes you have a constant gradient, not along an interval, but at a certain point. For example, when we have this, the function from here on the left is decreasing until this point, and after this point it starts increasing. This point is a minimum of the function, a local minimum, because maybe at the entire domain of the function there may be a lower value. At this point we have gradient that is equal to 0, and at this certain point the function is a constant. The first derivative will be 0 at this point. To the left of this point, the function is decreasing, so we'll have negative values that become less and less negative until 0. And then from this point and to the right, the gradient becomes positive since the function starts increasing, and we will have an increase of the first derivative. So when we have a local minimum, this is local minimum, the first derivative is increasing from negative. At this minimum point it is 0, and then increasing to the positive values. The first derivative is increasing, so second derivative must be positive here, showing us that the first derivative is increasing. Another case is when we have local maximum. At this maximum point, the function is constant only for this point. We have a gradient that equals 0. This is local maximum. And here you can see that to the left of the maximum, the function is increasing. It has positive values, but the gradient decrease becomes less and less positive until 0 at the maximum point, and then the function starts decreasing and the gradient for the first derivative becomes negative. We don't know if this is exactly the shape of the first derivative, but we know that to the left of the maximum it must be positive and decreasing, and to the right of the maximum it must be negative and decreasing. And since the first derivative is decreasing, the second derivative must be negative. There are two more cases or shapes of a function where we have where the function is constant for a point. One of them look like this, and one of them look like this. These are called inflection points. This is positive inflection, and this is negative inflection. Here we have a point, and here where the gradient of the function is 0. The function is a constant for this point only. At the points of inflection, the direction doesn't change. Here, at the positive inflection, the function is always increasing, and on the negative inflection, the function is always decreasing. Direction doesn't change. What changes here, we can say, is the concavity. If I exaggerate here, you can see that to the left of the point of inflection, the function goes like this, and then changes to go like this. Concave down becomes concave, or changes to concave up. Here we have concave down. The gradient comes from large positive down to 0, and at the point of inflection the gradient is exactly 0, and from the point of inflection and to the right the gradient goes back and increases positively. So concave down becomes concave up. The negative inflection point, it's just the opposite. The gradient is always negative. To the left of the inflection point, we can see that it is going up to 0, coming from large negative values up to smaller and smaller negative values until 0. Okay, we have concave up here, and at the point of inflection it is exactly 0, and to the right of the inflection we can see that it becomes negative, larger and larger. We have concave down. The first derivative looks like this. When we have positive inflection, the gradient is positive, that goes down to 0. This is the point of inflection, and after this point of inflection it goes up again. For the negative inflection, we have large negative that becomes lower and lower, negative gradient, until it is 0 at the point of inflection. Okay, these are the points of inflection. And after we pass the point of inflection, the gradient becomes larger and larger, negative. This is the first derivative for the point of inflection. what can we say about the second derivative here? The second derivative is the derivative of the first derivative, and we can see that at the point of inflection, this is minimum or maximum. The second derivative will be 0. 0 and 0. So this will help us next to find points of inflection and to find minimum and maximum. So if we know that the first derivative is 0, we know that we have either minimum or maximum, they are called turning points, or inflection points. How do we differ between turning points and inflection points? We will use the second derivative. In all these stationary points where the function is constant, the first derivative is 0. For the minimum, second derivative is positive. For the maximum, second derivative is negative. And for inflection points, second derivative is 0. Let's look at other cases where we have inflection point that is not stationary. Okay, we can have this. This is an inflection point where the gradient is not 0. Look what happens to the gradient. It's positive. The direction doesn't change. The function is always increasing. The gradient goes, it's positive, that goes down until some minimum point here, and then starts increasing again. First derivative will look like this. It starts with large positive, goes down to some minimum, and then up again. This is the inflection point. Positive inflection can also look like this. First concave up, and then concave down. Here is the inflection point. You have this, for example, in the sine and cosine graphs. Here you can see that we have positive gradient that is growing until inflection point. It's some maximum and then going down again. It will look like this. Going to some maximum positive value and then decreasing again. Negative inflection is when the function is decreasing. It could go like this. First concave up and then concave down. You can see that the gradient is going up here towards some maximum value and then back to large negative values. It looks like this. Some maximum, which is not 0 as in the previous inflections. And it could go this way, first concave down and then concave up. You can see that the gradient goes down to some minimum and then up again. And the minimum is just not 0. And all the values are negative since the function is decreasing. The second derivative in all these cases, in all these inflection points, is 0, since these are minimum or maximum of the first derivative. So the second derivative will be 0 for all inflection points. When we look for inflection points, we will look for the values where second derivative equals 0. In order to summarize everything, we will look at this diagram that shows all stationary and inflection points. The stationary points is where first derivative equals 0. It means that the gradient of the function is 0. It could be minimum or maximum. That's turning points, where the direction changes. Increase becomes decrease, or decrease becomes increase. And stationary could also be inflection points, where the direction doesn't change, even though the gradient is 0. What changes here is the concavity. Up becomes down, or concave down becomes concave up. Inflection points are all the points where the concavity changes. These are stationary inflections, the two ones in the middle where the gradient is 0, but there are inflection points where gradient is not 0 and still concave up changes to concave down or down to up. All this will help us to find inflection points and stationary point and to have an impression on the graph of the function even without drawing it, or it will help us draw or sketch the graph of the function. Thank you for listening. We will have more practice.